Chapter 12, Part 4 of Volume 2 of Airplane Flying Handbook, FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Dale Latham. Airplane Flying Handbook by the FAA. Engine failure during flight. Engine failures well above the ground are handled differently than those occurring at lower speeds and altitudes. Cruise airspeed allows better airplane control, and altitude may permit time for a possible diagnosis and remedy of the failure. Maintaining airplane control, however, is still paramount. Airplanes have been lost at altitude due to an apparent fixation on the engine problem to the detriment of flying the airplane. Not all engine failures or malfunctions are catastrophic in nature. Catastrophic meaning a major mechanical failure that damages the engine and precludes further engine operation. Many cases of power loss are related to fuel starvation, where restoration of power may be made with the selection of another tank. An orderly inventory of gauges and switches may reveal the problem. Carburetor heat or alternate air can be selected. The affected engine may run smoothly on just one magneto or at a lower power setting. Altering mixture may help. If fuel vapor formation is suspected, fuel boost pump operation may be used to eliminate flow and pressure fluctuations. Although it is a natural desire among pilots to save an ailing engine with a precautionary shutdown, the engine should be left running if there is any doubt as to needing it for further safe flight. Catastrophic failure accompanied by heavy vibration, smoke, blistering paint, or large trails of oil, on the other hand, indicate a critical situation. The affected engine should be feathered and the securing failed engine checklist completed. The pilot should divert to the nearest suitable airport and declare an emergency with ATC for priority handling. Fuel cross-feed is a method of getting fuel from a tank on one side of the airplane to an operating engine on the other. Cross-feed is used for extended single-engine operation. If a suitable airport is close at hand, there is no need to consider cross-feed. If prolonged flight on a single engine is inevitable due to airport non-availability, then cross-feed allows use of fuel that would otherwise be unavailable to the operating engine. It also permits the pilot to balance the fuel consumption to avoid an out-of-balance wing heaviness. AFM/POH procedures for cross-feed vary widely. Thorough fuel system knowledge is essential if cross-feed is to be conducted. Fuel selector positions and fuel boost pump usage for cross-feed differ greatly among multi-engine airplanes. Prior to landing, cross-feed should be terminated and the operating engine returned to its main tank fuel supply. If the airplane is above its single-engine absolute ceiling at the time of engine failure, it will slowly lose altitude. The pilot should maintain VYSE to minimize the rate of altitude loss. This drift down rate will be greatest immediately following the failure and will decrease as the single-engine ceiling is approached. Due to the performance variations caused by engine and propeller wear, turbulence, and pilot technique, the airplane may not maintain altitude even at its published single-engine ceiling. Any further rate of sink, however, would likely be modest. An engine failure in a descent or other low-power setting can be deceiving. The dramatic yaw and performance loss will be absent. At very low power settings, the pilot may not even be aware of a failure. If a failure is suspected, the pilot should advance both engine mixtures, propellers, and throttles significantly to the takeoff settings if necessary to correctly identify the failed engine. The power on the operative engine can always be reduced later. Engine inoperative approach and landing. The approach and landing with one engine inoperative is essentially the same as a two-engine approach and landing. The traffic pattern should be flown at similar altitudes, airspeeds, and key positions as a two-engine approach. The differences will be the reduced power available and the fact that the remaining thrust is asymmetrical. A higher than normal power setting will be necessary on the operative engine. With adequate airspeed and performance, the landing gear can still be extended on the downwind leg, in which case it should be confirmed down, no later than abeam the intended point of landing. Performance permitting, initial extension of wing flaps, 10 degrees typically, and descent from pattern altitude can also be initiated on the downwind leg. The airspeed should be no lower than VYSE. The direction of the traffic pattern, and therefore the turns, is of no consequence as far as airplane controllability and performance are concerned. It is perfectly acceptable to make turns toward the failed engine. On the base leg, if performance is adequate, the flaps may be extended to an intermediate setting, 25 degrees typically. If the performance is inadequate, as measured by decay in airspeed or high sink rate, delay further flap extension until closer to the runway. VYSE is still the minimum airspeed to maintain. On final approach, a normal 3-degree glide path to a landing is desirable. VASI or other vertical path lighting aids should be utilized if available. Slightly steeper approaches may be acceptable. However, a long, flat, low approach should be avoided. Large, sudden power applications or reductions should be avoided. Maintain VYSE until the landing is assured, then slow to 1.3 VSO or the AFM/POH recommended speed. The final flap setting may be delayed until the landing is assured, or the airplane may be landed with partial flaps. The airplane should remain in trim throughout. The pilot must be prepared, however, for a rudder trim change as the power of the operating engine is reduced to idle in the roundout just prior to touchdown. With drag from only one windmilling propeller, the airplane will tend to float more than on a two-engine approach. Precise airspeed control, therefore, is essential, especially when landing on a short, wet, or slippery surface. Some pilots favor resetting the rudder trim to neutral on final and compensating for yaw by holding rudder pressure for the remainder of the approach. This eliminates the rudder trim change close to the ground as the throttle is closed during the roundout for landing. This technique eliminates the need for groping for the rudder trim and manipulating it to neutral during final approach, which many pilots find to be highly distracting. AFM/POH recommendations or personal preference should be used. Single-engine go-arounds must be avoided. As a practical matter in single-engine approaches, once the airplane is on final approach with the landing gear and flaps extended, it is committed to land. If not on the intended runway, then on another runway, a taxiway, or grassy infield. The light twin does not have the performance to climb on one engine with landing gear and flaps extended. Considerable altitude will be lost while maintaining VYSE and retracting landing gear and flaps. Losses of 500 feet or more are not unusual. If the landing gear has been lowered with an alternate means of extension, retraction may not be possible, virtually negating any climb capability. Engine inoperative flight principles. Best single-engine climb performance is obtained at VYSE with maximum available power and minimum drag. After the flaps and landing gear have been retracted and the propeller of the failed engine feathered, a key element in best climb performance is minimizing side slip. With the single-engine airplane, or a multi-engine airplane with both engines operative, side slip is eliminated when the ball of the turn and bank instrument is centered. This is a condition of zero side slip, and the airplane is presenting its smallest possible profile to the relative wind. As a result, drag is at its minimum. Pilots know this as coordinated flight. In a multi-engine airplane with an inoperative engine, the center ball is no longer the indicator of zero side slip due to asymmetrical thrust. In fact, there is no instrument at all that will directly tell the pilot the flight conditions for zero side slip. In the absence of a yaw string, minimizing side slip is a matter of placing the airplane at a predetermined bank angle and ball position. The AFM/POH performance charts for single-engine flight were determined at zero side slip. If this performance is even to be approximated, the zero side slip technique must be utilized. There are two different control inputs that can be used to counteract the asymmetrical thrust of a failed engine. One, yaw from the rudder, and two, the horizontal component of lift that results from bank with the ailerons. Used individually, neither is correct. Used together in the proper combination, zero side slip and best climb performance are achieved. Three different scenarios of airplane control inputs are presented below. Neither of the first two is correct. They are presented to illustrate the reasons for the zero side slip approach to best climb performance. 1. Engine inoperative flight with the wings level and ball centered requires large rudder inputs towards the operative engine. See Figure 12-16. The result is a moderate side slip towards the inoperative engine. Climb performance will be reduced by the moderate side slip. With wings level, VMC will be significantly higher than published, as there is no horizontal component of lift available to help the rudder combat asymmetrical thrust. 2. Engine inoperative flight using ailerons alone requires an 8 to 10 degree bank angle towards the operative engine. See Figure 12-17. This assumes no rudder input. The ball will be displaced well towards the operative engine. The result is a large side slip towards the operative engine. Climb performance will be greatly reduced by the large side slip. 3. Rudder and ailerons used together in proper combination will result in a bank approximately 2 degrees towards the operative engine. The ball will be displaced approximately 1/3 to 1/2 towards the operative engine. The result is zero side slip and maximum climb performance. See Figure 12-18. Any attitude other than zero side slip increases drag, decreasing performance. VMC, under these circumstances, will be higher than published, as less than 5 degree bank certification limit is employed. The precise condition of zero side slip, bank angle, and ball position varies slightly from model to model and with available power and airspeed. If the airplane is not equipped with counter-rotating propellers, it will also vary slightly with the engine failed due to P factor. The foregoing zero side slip recommendations apply to reciprocating engine multi-engine airplanes flown at VYSE with the inoperative engine feathered. The zero side slip ball position for straight flight is also the zero side slip position for turning flight. When bank angle is plotted against climb performance for hypothetical twin, zero side slip results in the best, however marginal, climb performance or the least rate of descent. Zero bank, all rudder to counteract yaw, degrades climb performance as a result of moderate side slip. Using bank angle alone, no rudder, severely degrades climb performance as a result of a large side slip. The actual bank angle for zero side slip varies among airplanes from 1 1/2 to 2 1/2 degrees. The position of the ball varies from 1/3 to 1/2 of a ball width from instrument center. For any multi-engine airplane, zero side slip can be confirmed through the use of a yaw string. A yaw string is a piece of string or yarn approximately 18 to 36 inches in length, taped to the base of the windshield or to the nose near the windshield along the airplane centerline. In two-engine coordinated flight, the relative wind will cause the string to align itself with the longitudinal axis of the airplane and will position itself straight up the center of the windshield. This is zero side slip. Experimentation with slips and skids will vividly display the location of the relative wind. Adequate altitude and flying speed must be maintained while accomplishing these maneuvers. With an engine set to zero thrust, or feathered, and the airplane slowed to VYSE, a climb with maximum power on the remaining engine will reveal the precise bank angle and ball deflection required for zero side slip and best climb performance. Zero side slip will again be indicated by the yaw string when it aligns itself vertically on the windshield. There will be very minor changes from this attitude depending upon the engine failed, with non-counter-rotating propellers, power available, airspeed and weight, but without more sensitive testing equipment, these changes are difficult to detect. The only significant difference would be the pitch attitude required to maintain VYSE under different density altitude, power available, and weight conditions. If a yaw string is attached to the airplane at the time of a VMC demonstration, it will be noted that VMC occurs under conditions of side slip. VMC was not determined under conditions of zero side slip during aircraft certification, and zero side slip is not part of a VMC demonstration for pilot certification. To review, there are two different sets of bank angles used in one-engine inoperative flight. To maintain directional control of a multi-engine airplane suffering an engine failure at low speeds, such as climb, momentarily bank at least below 5 degrees and a maximum of 10 degrees towards the inoperative engine as the pitch attitude for VYSE is set. This maneuver should be instinctive to the proficient multi-engine pilot and take only 1 to 2 seconds to attain. It is held just long enough to assure directional control as the pitch attitude for VYSE is assumed. To obtain the best climb performance, the airplane must be flown at VYSE and zero side slip, with the failed engine feathered and maximum available power from the operating engine. Zero side slip is approximately 2 degrees of bank toward the operating engine and a 1/3 to 1/2 ball deflection, also toward the operating engine. The precise bank angle and ball position will vary somewhat with make and model and power available. If above the airplane's single-engine ceiling, this attitude and configuration will result in the minimum rate of sink. In OEI flight at low altitudes and airspeeds such as the initial climb after takeoff, pilots must operate the airplane so as to guard against the 3 major accident factors. 1. Loss of directional control. 2. Loss of performance. And 3. Loss of flying speed. All have equal potential to be lethal. Loss of flying speed will not be a factor, however, when the airplane is operated with due regard for directional control and performance. Slow flight. There's nothing unusual about maneuvering during a slow flight in a multi-engine airplane. Slow flight may be conducted in straight and level flight, turns, in the clean configuration, landing configuration, or at any other combination of landing gear and flaps. Pilots should closely monitor cylinder head and oil temperatures during slow flight. Some high-performance multi-engine airplanes tend to heat up fairly quickly under some conditions of slow flight, particularly in the landing configuration. Simulated engine failure should not be conducted during slow flight. The airplane will be well below VSSE and very close to VMC. Stability, stall warning, or stall avoidance devices should not be disabled while maneuvering during slow flight. Stalls. Stall characteristics vary among multi-engine airplanes just as they do with single-engine airplanes, and therefore it is important to be familiar with them. The application of power upon stall recovery, however, has a significantly greater effect during stalls in a twin than a single-engine airplane. In the twin, an application of power blows large masses of air from the propellers directly over the wings, producing a significant amount of lift in addition to the expected thrust. The multi-engine airplane, particularly at light operating weights, typically has a higher thrust-to-weight ratio, making it quicker to accelerate out of a stalled condition. In general, stall recognition and recovery training in twins is performed similar to any high-performance single-engine airplane. However, for twins, all stall maneuvers should be planned so as to be completed at least 3,000 feet AGL. Single-engine stalls, or stalls with significantly more power on one engine than the other, should not be attempted due to the likelihood of a departure from controlled flight and possible spin entry. Similarly, simulated engine failures should not be performed during stall entry and recovery. Power-off stalls. Approach and landing. Power-off stalls are practiced to simulate typical approach and landing scenarios. To initiate a power-off stall maneuver, the area surrounding the airplane should first be cleared for possible traffic. The airplane should then be slowed and configured for an approach and landing. A stabilized descent should be established, approximately 500 FPM, and trim adjusted. The pilot should then transition smoothly from the stabilized descent attitude to a pitch attitude that will induce a stall. Power is reduced further during this phase, and trimming should cease at speeds slower than takeoff. When the airplane reaches a stalled condition, the recovery is accomplished by simultaneously reducing the angle of attack with coordinated use of the flight controls and smoothly applying takeoff or specified power. The flap setting should be reduced from full to approach, or as recommended by the manufacturer. Then, with the positive rate of climb, the landing gear is selected up. The remaining flaps are then retracted as climb has commenced. This recovery process should be completed with a minimum loss of altitude appropriate to the aircraft characteristics. The airplane should be accelerated to VX if simulated obstacles are present, or VY during recovery and climb. Considerable forward elevator, stabilator, pressure will be required after the stall recovery as the airplane accelerates to VX or VY. Appropriate trim input should be anticipated. Power-off stalls may be performed with wings level or from shallow and medium bank turns. When recovering from a stall performed from turning flight, the angle of attack should be reduced prior to leveling the wings. Flight control inputs should be coordinated. It is usually not advisable to execute full stalls in multi-engine airplanes because of their relatively high wing loading. Stall training should be limited to approaches to stalls and when a stall condition occurs. Recoveries should be initiated at the onset or decay of control effectiveness or when the first physical indication of the stall occurs. Power-on stalls. Takeoff and departure. Power-on stalls are practiced to simulate typical takeoff scenarios. To initiate a power-on stall maneuver, the area surrounding the airplane should always be cleared to look for potential traffic. The airplane is slowed to the manufacturer's recommended liftoff speed. The airplane should be configured in the takeoff configuration. Trim should be adjusted for the speed. Engine power is then increased to that recommended in the AFM/POH for the practice of power-on stalls. In the absence of a recommended setting, use approximately 65% of maximum available power while placing the engine in a pitch attitude that will induce a stall. Other specified, reduced, power settings may be used to simulate performance at higher gross weights and density altitudes. When the airplane reaches a stalled condition, the recovery is made by simultaneously lowering the angle of attack with coordinated use of the flight controls and applying power as appropriate. However, if simulating limited power available for high gross weight and density altitude situations, the power during the recovery should be limited to that specified. The recovery should be completed with a minimum loss of altitude appropriate to aircraft characteristics. The landing gear should be retracted when a positive rate of climb is attained and flaps retracted if flaps were set for takeoff. The target airspeed on recovery is Vx if, simulated, obstructions are present, or Vy. The pilot should anticipate the need for nose-down trim as the airplane accelerates to Vx or Vy after recovery. Power-on stalls may be performed from straight flight or from shallow and medium banked turns. When recovering from the power-on stall performed from turning flight, the angle of attack should be reduced prior to leveling the wings and the flight control inputs should be coordinated. Spin awareness. No multi-engine airplane is approved for spins, and their spin recovery characteristics are generally very poor. It is therefore necessary to practice spin avoidance and maintain a high awareness of situations that can result in an inadvertent spin. In order to spin any airplane, it must first be stalled. At the stall, a yawing moment must be introduced. In a multi-engine airplane, the yawing moment may be generated by rudder input or asymmetrical thrust. It follows, then, that spin awareness be at its greatest during VMC demonstrations, stall practice, slow flight, or any condition of high asymmetrical thrust, particularly at low speed, high angle of attack. Single-engine stalls are not part of any multi-engine training curriculum. A situation that may inadvertently degrade into a spin entry is a simulated engine failure introduced at an inappropriately low speed. No engine failure should ever be introduced below safe, intentional one-engine inoperative speed, VSSE. If no VSSE is published, use VYSE. The necessity of simulating engine failures at low airspeeds is erroneous. Other than training situations, the multi-engine airplane is only operated below VSSE for mere seconds, just after liftoff, or during the last few dozen feet of altitude in preparation for a landing. For spin avoidance, when practicing engine failures, the flight instructor should pay strict attention to the maintenance of proper airspeed and bank angle as the student executes the appropriate procedure. The instructor should also be particularly alert during the stall and slow flight practice. Forward center of gravity positions result in favorable stall and spin avoidance characteristics, but do not eliminate the hazard. When performing a VMC demonstration, the instructor should also be alert for any sign of an impending stall. The student may be highly focused on the directional control aspect of the maneuver to the extent that impending stall indications go unnoticed. If a VMC demonstration cannot be accomplished under existing conditions of density altitude, it may, for training purposes, be done utilizing the rudder blocking technique described in the following section. As very few twins have ever been spin tested, none are required to, The recommended spin recovery techniques are based only on the best information available. The departure from controlled flight may be quite abrupt and possibly disorienting. The direction of an upright spin can be confirmed from the turn needle or the symbolic airplane of the turn coordinator if necessary. Do not rely on the ball position or other instruments. If a spin is entered, most manufacturers recommend immediately retarding both throttles to idle, applying full rudder opposite the direction of rotation, and applying full forward elevator stabilator pressure with ailerons neutral. These actions should be taken as near simultaneously as possible. The controls should then be held in that position. Recovery, if possible, will take considerable altitude. The longer the delay from entry until taking corrective action, the less likely that recovery will be successful. End Chapter 12, Part 4. Recording by Dale Latham.